Magnets are weird. We're talking about real-life telekinesis. How can they just pull stuff? Why can they pull this kind of stuff, but not this kind of stuff? And why is the entire Earth a magnet? Well, first, we need to start with the basics. Magnets have two sides, north and south. North loves south, but north really hates north. So it's kind of like a Romeo and Juliet situation, but if everyone was Romeo and Juliet. But why are these named after directions? Well, if you freely suspend one of these suckers, one side will point to the north and the other to the south. Which is kind of funny, because if opposites attract, that means the Earth's magnetic pole has the north in the south and the south in the north. And that's not confusing at all. What if you take two magnets and point them in the opposite direction at, say, a piece of metal? Well, they start beefing so hard, they actually forget about the metal altogether and cancel each other out. Okay, but what actually is it? Magnets, just like pretty much everything else that's ever existed, is made up of atoms. So what makes these atoms have the force and these atoms totally lame? Their differences can actually be found in their similarity. All atoms have stuff called electrons, which orbit the middle/nucleus of the atom. Atoms also have stuff in the middle called protons. There's also neutrons, but they're kind of completely useless for magnetism purposes and total bums. That's because protons and electrons have charge, and when charge is moving, that charge becomes a mini little magnet. Remember that. It's gonna be important later. So while the proton might not be moving, the electron is, making magnetism. Right? No, because I totally just lied to you, you gullible goose. Electrons don't orbit the middle of the atom at all. They actually just teleport around in little clouds in all directions, which is weird and a whole other scientific beast maybe for another video. The gist is, they don't move enough to really be magnetic. But that's okay, because this guy, named Otto Stern, thought up a really complicated experiment that proves each electron is actually a teeny magnet in and of itself. Pause. What the freak? Why is an electron a teeny magnet in and of itself? Well, that's kind of a hard question because no one really knows. The answer is, it just is. We spawned in here and it was just like that. And that is literally the best answer physics can give. Okay, but then if normal stuff is made up of magnetic stuff, why the flip isn't everything magnetic? Well, to answer that question, we have to ask a bonus question. Why is the periodic table such a dumb shape? Ding, ding, ding. Valence electrons. Valence electrons are the electrons on the outer shell, which is also called an energy level. Why is this important? Well, remember how I was explaining earlier that two magnets facing the opposite way cancel out and don't do anything? The same exact thing happens here. Half of the electrons in an energy level can be facing the same direction. Once you hit halfway, the rest of the electrons have to be facing the opposite direction because that's just how spinning particles like electrons interact. Let me show you an example. Let's pluck one of the energy levels that can hold 8 electrons. Throw one electron in there and the atom has a magnetism of 1 electron. Easy enough. Throw another and the atom has the magnetism of 2 electrons. That math checks out. Another and it's 3. Another we get 4, but throw one more electron in there, and because it's past the halfway point, the electron faces the opposite direction, canceling out the other electrons. So now your atom only has the magnetism of 3 electrons. Throw in another and you get 2, down to 1, fill it all the way, and your atom is no longer magnetic at all. So that means atoms with almost full or almost empty energy levels have pretty much no magnetism, which in turn means that stuff made up by these atoms in the periodic table are not even capable of being significantly magnetic. And we're left with this stuff. You might have noticed some of this stuff isn't even metal, let alone magnetic. That's because thus far we have only discussed the magnetism of a single atom, which, surprise, surprise, is basically nothing. You need a lot of magnetic atoms pointing in the same direction in order to have any sort of magnetism at all, which means all of these nearby atoms have to cluster and work together. These clusters/crystals fall under one of two categories: ferromagnetic and antiferromagnetic, aka yes magnetism and no magnetism. Again, back to basic magnetic principles. Ferromagnetic crystals have the atoms all facing the same way, while atoms in the antiferromagnetic are all flipped, canceling each other out. Finally, we found them. Our super special magnetic stuff. But even though something like iron is ferromagnetic, your typical stainless steel spoon isn't automatically magnetic. It's magnetic when it's touching a magnet, but not magnetic by default. Why? Well, sure, you might have magnetic electrons that make up magnetic atoms that make up magnetic crystals. These crystals aren't always pointing their magnetism the same way. Because they're all grouped up, this crystal might be pointing this way, but a different group over here might be pointing that way. Do that a couple more times and everyone ends up canceling each other out. But if you put this spoon up to a magnet, all of the crystals get attracted, so the north all point up and the south all point down, making the spoon magnetic. Satisfied?